Let's take a look here at example 4 and see how we can build upon the ideas we talked about in the last video. Notice here that example 4 is going to be exactly the same as what we had in example number 2. We're going to have the same f. We still want to find the flux of f across sigma, where sigma is part of the paraboloid that lies above the square, and again, we're going to imagine that it has upward orientation. That is, we're imagining that I'm tracking fluid flowing in this direction through the surface as positive flow. Okay, well, in example number 2, we found a parameterization of our surface and dealt with the problem that way and arrived at an answer. But here, we want to notice that we have a function defining our surface, and that gives us an alternative way of tackling this question. So I'll start by saying we see that sigma is defined by a function z equals, and I'll say a g of xy. G of xy here represents my 4 minus x squared minus y squared. So because of this, how about we go ahead and create our capital G that we talked about in the last video. Remember, that's going to just be z minus my g of xy, which in this case would be z minus, and I would have 4 minus x squared minus y squared. Of course, if I wanted to write that out one more time, that would just look like z minus 4 plus an x squared plus a y squared. Okay, so let's see what we have here. Remember now that we can go ahead and state that the flux integral that we wanted to calculate, which looked like this, we could now, because we have a function, rewrite it to look like f dotted with the gradient of g over my region of D. Of course, my dA represents dx dy in some order. So let's see what we have here, and just make sure that this needs to be gradient g as opposed to negative gradient g. So let's see what we come up with. So this would look like my f is going to have x, y, y, z, z, x, and the gradient is going to be, let's see, partial with respect to x should be 2x, partial with respect to y should be 2y, and partial with respect to z here should be 1. So again, since I need to have upward orientation, that means I need to have a positive z. So this vector will slope upwards, and I do have a positive z. Again, if I multiplied this by a negative 1, I would have a negative z component, and I'd get a vector that points downward. I don't want that. So this looks like a perfect setup for what we need. I'm going to go ahead and arbitrarily say here that let's just do dx dy, and my x bounds go from 0 to 1, y goes from 0 to 1. So if I was to compute this dot product here, I could easily go ahead and see then how difficult the remaining integral is supposed to be. Okay, so let's see. I'm going to do 2x times my xy, so that's 2x squared y. I'm then going to do plus, I'm going to have 2y squared z, and then I'm finally going to have zx and dx dy. All right, well, there's a slight complication to what we have here, a very slight one. Notice that the variables that I'm integrating with respect to here are x and y. So I can't really have z's in here, because like, what am I supposed to do with them? But again, because I have a function at the start, I know what every z is equivalent to. So if I rewrite this one final time, I can see that this should actually look like 2x squared y plus 2y squared, and then z is 4 minus x squared minus y squared, plus z, 4 minus x squared minus y squared, times x. And I have all of this. Now, again, what we've done here that hopefully should be simpler is we've avoided having to find a parameterization for the surface. And the way that we were able to do that again is because I started with a function of z equals. So once I have that, this new approach, of course, becomes available. Now, I'm not going to go ahead and work through all the details of this integral right here, but I'll ask you to go ahead and do it before you move on to the next video. And I think you should be able to guess what that final answer is going to be. Because if this is exactly the same as example number 2, and all we've changed is the approach, I better get that exact same answer of 713 over 180. I'd ask you to go ahead and actually try that out and make sure that you actually do arrive at the same answer.